Hello and welcome to Lesson 8.3 on Common Logarithms. Today's goals are going to be to solve exponential equations by using what's called a common logarithm. Common logarithm just means a logarithm with a base of 10. It's what the calculator does when you press log on it. So most kind of like computer programs that are going to do logarithms for us are going to be assuming we're using a base of 10. So they're going to be assuming we're asking like 10 raised to what power equals x. We're also going to try to evaluate logarithmic expressions by using the change of base formula, which is going to allow us to work with logs that are not common logarithms, that have different bases. Logarithms, have you seen before, are basically the inverse functions to exponentials. So the way that I think about, the usefulness of logarithms is if you're doing algebra, if you're trying to do some kind of solution describing something in the world, and you've got multiplication going on, well, you're going to need to know how to do division in order to solve that equation. So like if you have x equals 3 times y, in order to solve for y, you're going to have to divide both sides by 3. So if your expression has multiplication in it, you're going to need the tool of division to undo that, right? If your expression has addition, you'll need the tool of subtraction and vice versa. If your expression has an exponent, if it has repeated multiplication expressed as an exponent, you're going to need a certain tool to undo that. And that tool is the mathematical idea of the logarithm. Logarithm is just the anti-exponent. When we have equations and we try to find their inverses, the graphs that we produce are generally reflections over the line y equals x. So if I say like y equals 3x, y equals x, and y equals 1/3 x. Well, the red line and the green line here are reflections over the blue line. The blue line is my 45-degree angle, y equals x line. And these two are inverse equations. They're just reflections over this line. So, the upper part gets reflected, the lower part gets reflected. And if we want to get those algebraically, so if we have y equals 3x, and I want to algebraically get my other equation, like where did that 1/3 x come from? You'd recall that the steps would be that you switch your x and y values. So you get x equals 3y. And then we solve for y. So we divide each side by 3. If you want to say you multiply each side by 1/3, and you get your solution. Y equals 1/3 x. Right? And that makes sense because what we're doing is we are literally just switching our x and y values on the graph. So for example, instead of the point 2, 6, we get the point 6, 2. Right? So that's a key thing on these inverse graphs, is that your x and y values should flip. You should have all the same coordinates, but those coordinates should have flipped x and y values. All right, so that's what we kind of expect with exponents and logarithms. So if I show the graph for 10 to the x, right, where x is our exponent and 10 to the x is the product of that exponent, well then 10 to the 0 is 1, 10 to the first is 10, 10 to the second is 100, 10 to the third is 1,000. Let me change the axes here just for a moment so we can see it a little better. So that would be this red line. So 10 to the 0 is 1, 10 to the first power is 10, 10 to the second power is 100. On our inverse graph, we have all those same points, but in reverse. So when our x value is 1, so not our output, but our input is 1, our output is 0. When our input is 10, our output is 1. When our input is 100, our output is 2. So when we're looking at the exponential graph, what x represents is the exponent, right? The exponent is the x value. When we're looking at a logarithmic graph, the exponent is the y value. The height of the graph is the exponent. Whereas in the exponential graph, the y value, right, our output, is the product that we get when we take our base to some exponent, right? This is our product that we get, 1, 10, 100, 1,000, 10,000. In the logarithmic graph, the y value, or sorry, it's the x value that is that product, right? So this conceptually, all that we're doing is we're just reversing exponential ideas. We're just doing it in the opposite order. Now, what gets really tricky is that when we do this, the thing that I always find hard, the thing that always causes my brain to kind of shut down a little bit on logarithms is that you don't read them left to right, right? So in the first two lessons this week, you would have seen that what we're doing when we do logarithms is we kind of read them in a funky order. That's just based off how the notation was created. So if I say log base 10 of 100, the answer is 2. And what this statement is saying is that 10 to the second power equals 100. Right? So if I did log base 10 of 1000, that should equal 3 because 10 to the third power is 1000. So that's the thing that with logarithms always just is the biggest hurdle to get over, is just we're so used to reading left to right within like an English writing system, that this idea of like I'm going to read left, skip a number, and then go back into the middle, it's just hard. It's just a pattern that we've gotten ingrained in our head that's really hard to break. So conceptually, the logarithms are not too far out there as far as a math concept goes. It's really just the notation itself that is the stumbling block for most people. So it's just important that you kind of work on feeling comfortable with this notation and how you want to read it. Now, this notation is going to, part of it's going to disappear here on today's lesson. So with common logarithms, we are just assuming that we have a base of 10 if there is no other base written. So if you see log 1000, then we're actually adding an additional step to kind of the mental hurdles we have to jump over. We need to remember that there's a 10 here, right? So there's kind of this implicit 10 here, and that implicit 10 is the base of the exponent, right? 10 to the third is what this logarithm is representing, and the 1000 is representing the answer. Now, since we're dealing with logarithms, we're not really going in this direction. We're starting with the answer, and we're kind of working backwards where our solution is the exponent. Okay, so that's one major thing to remember, is just that the solution to these logarithms is the exponent in an exponential expression. So let's go back to the for a minute. So, okay, let's just read through this. The common logarithms of numbers that differ by integral powers of 10 are closely related. Remember that a logarithm represents an exponent. For example, in the equation y equals log of x, y is the power to which 10 is raised to obtain the value of x. Complete the table below. So we have log of 1 equals 0. Okay, and that's because 10 to the 0th power equals 1. Log of 10 equals 1. Remember, these right side, these are the exponents. So 10 to the first power equals 10. And the x value here is the product of that exponential. So log of 100, we're kind of trying to undo 100 in terms of exponentials. Well, it's 10 to the second power. This one's a little tricky to conceptualize, but they're saying log of 10 to the m equals m because 10m equals 10m. So they're saying if we had the base of 10 down here was written in, we'd be saying 10 to the m. Well, we don't have a value for that because it's a variable, so that just equals 10 to the m. Okay, one final thing before we move on to an example. If we want to do the inverse equation in the same way that we've done it before. So by which I mean we want to switch the x and y values, right? Switch the x and y values and solve for y. This is kind of what these steps would look like. So we'd switch the x and y values. Now we're trying to solve for y to get our inverse equation. Well, in order to get that y down, there's a property that we use, and this is one of the useful properties of logarithms in just kind of manipulating algebraic expressions. There's a property of the logarithm that says that when we take a logarithm, the exponent can move down into the front. In your first two lessons, you probably would have seen examples of this happening and kind of descriptions of why this works. Once we're here, this section, if we just look at that in isolation, log or implied base of 10. Well, what's the solution? This one, this is saying 10 to what power equals 10? Well, it's to the first power. So log of 10 is just 1. So that part is going to go away, and we're just going to have y equals log of x. Okay, so this is how we reach this equation by doing those steps that we're used to of switching the x and y values. Now, if you notice on the second step, this is kind of summarizing what we're expecting from our graph. Our graph shows exponent values on the y-axis, right? The y-axis is representing the exponent values, whereas before, in an exponential equation, it was the x values that were representing the exponent. Okay, if I go back to my graph here, okay, looking at our graph of the two functions, the exponential function, x is the exponent, and in the logarithmic function, y is the exponent. Okay, so anyways, I think this is a fairly tricky topic in my opinion, and it's just it's because of those kind of like hurdles where you kind of have to just mentally jump around with what you're saying, and it's not entirely intuitive for me anyways to keep in mind what each part of the logarithmic equation is referring to. But the summary of it is that the right side, the y value, is referring to the exponent in an exponential equation, and the x value, the thing that you're taking the log of, is the answer of an exponential expression, right? Because if you just think in terms of we're trying to undo exponentials, if you think of like, what do I make when I have an exponential equation? Okay, I have 10 raised to some power, 10 to the third power equals 1,000. If I want to go in reverse, I'm going to have to start with that 1,000 and head in the opposite direction. So, or if we want to do 10 to the second power, so 10 to the second power equals 100. If I want to go in reverse, I'm going to have to take that 100 and do something to it. What I'm going to do to it is the logarithm manipulation, the logarithm function. Okay, example one here, we're not going to make a separate video because it's literally just plug something into your calculator. It says use a calculator to evaluate log 8 to the nearest 10,000th. So log 8, the way we do that, we go to a calculator, just type in the log button and 8, and it'll give us the answer. So this means that 10 to the 0.903th power, if I wrote that out, 10 raised to this value, that's going to give me an answer of 8. That's what that's telling me. Most calculators are programmed to be common logarithms when you type in the log button, and we don't spend a lot of time doing logarithms by hand. I'd have to talk to some of the people who did math majors in college. I was doing a chemistry major that so required about 2 years of higher level math. Within that 2 levels of college math, I never did a logarithm by hand. I'm not quite sure. I wouldn't be too surprised if somebody did logarithms by hand that were actual math majors, but it was probably a pretty short lesson. I think that there's sort of a conclusion that within math there's a trade-off between how convenient it is to rely on the calculators at this point versus how complicated it might be to go through the steps of actually doing one of these by hand. There are ways to do logarithms by hands to actually find this value without needing a calculator. And if you're curious about that, feel free to look it up and kind of explore that at your own pace. I think that's an interesting topic. It's something that I'd like to do myself just to kind of shore up that part of information in my brain. But it's not something that I know right now, and it's not something that you guys are going to be expected to know this year or any time in college, or sorry, in high school. Okay, so we'll take a look at example number 2 in the next video.